Hey all, it's Barry, and I'm here to teach you some physics. These videos are meant to summarize a unit, and today we're hitting the intro unit for AP Physics 1, including vectors, graphs, and how to use proper units. So let's get to it. First thing we need to do is briefly recall our movie Despicable Me. We've got Vector right here, and he commits crime with both direction and magnitude. And that's a great way to get going with this, okay? As we look at vectors, it's important to remember that a vector does have both a direction and a magnitude. So we're going to mark our vector here for having both a magnitude and a direction. The scalar is going to be the opposite of that. It's just going to have a magnitude. Okay, this is really important when we think about the difference between these two and how we're going to utilize them in physics. And I want to go ahead and match up some of our options over here with what is what. So distance is going to be just a scalar because it, by definition, does not have a direction associated where displacement does, and that is the difference between those two terms. So we've got speed versus velocity also. It's going to be the same thing. Speed is like a speed limit. It says how fast you can go as a scalar, but it doesn't actually give you the direction that you have to drive in. Whereas velocity, something you might get from your GPS, it's telling you not just what direction to go, how fast you can go, all that stuff all together. Acceleration is going to be positive and negative, so it is going to have a vector as well. And as you see so far, I've used terms from the first unit, really. I'm going to throw energy in also, because energy is really interesting and something we will cover in later units, but it focuses more specifically on just how much energy is there and not in a direction in which it flows, so that is going to be considered a scalar. So as we keep going, we need to talk about how this magnitude and direction come together. First thing we need is our magnitude, which is going to be how long in terms of a vector the actual vector is, and the direction is going to be the direction that it points from tail to head. So let's keep all that in mind. This defines a full vector for us here. Now there's a couple different ways that we can look at the orientation of a vector. First would be the angle orientation, in which case we'd want to know the angle associated here from the horizontal. And we could just say that this theta right there would be the angle that it's oriented at. We could also go north, south, east, and west. So if we wanted to do that, we would start out going east here, and we would say, okay, this vector turned north based on that same angle that we would have marked before. Regardless, whenever you draw a diagram, make sure you're marking your theta on there and you have that associated with what's going on. And you see over here, this is more like the resultant that we're looking at right here, and that there is an x and y component to it that could also be marked as a north and an east component. That's really important as we keep moving here. So let's keep it going. We can put vectors together by using vector addition. We're going to have to do a couple things in order to do that. We have one vector here and another vector there, and then we're going to have a resultant vector that's going to be the total vector of the two of those combined. In order to find that total vector, we need to know both the x and the y components of this first vector, and the same for the second, the x and the y components. We're then going to take those x's and put them together to get this and this equal to this bottom line overall. We're then going to do the same thing for the y and put them together. And now we have the total x and y, and we can put all of it together as one whole final vector. So the first thing we did here was we separated, right, our x and our y components to see the differences here as we moved along. We then combined them, so it was x1 right there, x2 right there, y1, y2, and that combined to help us remake our full vector overall that goes right over the top. And you're going to have to use things like SOHCAHTOA and the Pythagorean theorem in order to do that. So keep that in mind as well. Next thing we need to look at are graphs of motion. Okay, a couple of things we need to think about when we look at a graph of motion. First, time is always going to be on the x-axis. That's what's always going to be there. Time is constant. It will be on the x-axis. Next, you need to look at what's on that y-axis. That's really, really important. It can be position, velocity, or acceleration when we're looking at graphs of motion. So that's going to help us say, okay, what's on this graph? Let's say we saw a position time graph. How does this describe the motion? Well, it's going to tell us what position something is at during a certain time. If it were a velocity time graph, it would tell us how fast it's going at that time. An acceleration time graph, whether or not the velocity is changing at that time. And this will tell us a lot about other factors as well. So if the velocity is changing, we know there's an acceleration. If the position is changing, we know that there's a velocity, so forth and so on, based on the definitions of these terms. Okay? Now, in order to properly utilize these, I'm going to look at these two graphs. And the question I put there right away is, are these the same graph? If you look at the shape right away, yep, Same graph, right? But let's look at these axes like we just mentioned. We've got our x-axis here and our x-axis here. Both of those are time. We mentioned time is always going to be what's on that axis. If we look at the y, we see position and velocity. So these are very differently going to be describing the motion of an object. I'm going to show you an example as to that. We're going to look at when it's standing still. Okay, this first object over here is going to be still when the position does not change. And that's going to happen right here. Okay, we see that the position stays the same at 60 meters from 10 to 15 seconds. No change in position is going to mean no motion. But if we move over to this other graph and look at where the position does not change, where there's no velocity, it's going to be where v on that y-axis equals 0, here and here and here. And those are the only spots that it's going to be happening there. Same curve for both these, very different way of interpreting those. So make sure you're looking at your axes and you know what's going on. All right, next thing we got to talk about is units. Units are vital when we talk about physics. Numbers are for math classes. Physics requires a descriptor for numbers. And this poor little guy right here is getting interviewed. And the interviewer says something along the lines of, what's the fastest you've gone on that bike? And he says, 30. And the interviewer says, 30 what? And he says, speed. And while that's not a bad thought for somebody his age, we don't want to describe something as 30 speed. We want to describe it with a unit that's useful. 30 miles an hour, 30 meters per second, something along those lines. So he does not properly portray his speed in this because he doesn't know how to use units for this. Something I tell all of my students, if you don't have units on your numbers, then I consider them bananas. So this kid would have told me his speed is 30 bananas. Not helpful in describing what he's actually doing. Last thing to mention here is units and how they can help you prove equations. We see one of our very first kinematic equations up here at the top. And I went ahead and took our basic units, and there'll be more on that in Unit 1, so you can check that next video out. But I went ahead and took our basic units for these different things, position, velocity, and acceleration, and I plugged them in. And so you see right there, position becomes its unit. Same thing here, so forth and so on. And all I've done is plug in the units for each of those different values. And in the end, we get meters equal meters plus meters again. And it proves that that equation works and should help with understanding there as well. So that's it. Thanks for being here for our very first one.